Okay, we'll start then. On the board, you'll see the number of the text for
Yeah.
attendance. Go ahead and do that if you haven't already done so. Also, it might be a good idea to either print the topic sheet out for today or at least have it available on your machine so you can refer to it as I go through the lecture. We have a lot of material to talk about tonight, so take good notes. Stop me at any point if you need to ask any questions, and I'll be happy to address the question. Just feel free to interrupt me. If you send me one of those messages to collaborate, I might not see it if I'm not looking at the computer screen. So just feel free to interrupt me. So we'll go ahead and start now. Get rid of this. All right. So welcome back to another lecture. Just to kind of go back and look at what we covered so far in the last time we met, we did an introduction. We talked about physical quantities, and we talked about the fact that to represent a quantity, it takes two pieces of information. You got to have a number, you got to have a unit. And so we talked about different ways of where if I have a number that's extremely big or a number that's extremely small, a convenient way to represent that number would be to use scientific notation. Kind of a subset of scientific notation is engineering notation. And if you put a number or quantity in engineering notation, then you can use that from that table of metric prefixes. You can substitute out the power of 10 that corresponds, the symbol that corresponds to the power of 10. You can write the number or the quantity in a more efficient way. So we talked about that. We also talked about measured numbers. And the second part of a physical quantity is the unit. We talked about systems of units, the fact that there are two. There is the English system, there's the metric system, and of course, the metric system has those subsystems that we referred to. And I think we ended by talking about measured numbers, accuracy, and precision. What I want to do today is I want to answer these three very important questions. What is voltage? What is current? And what is resistance? Now, these are the fundamental quantities that we'll deal with throughout the semester. These three, and there's two more, we'll also deal with power and we'll deal with energy, but these are the basic three. I call these the big three. And so what I want to do is talk about what these things are. What does it mean to say you have a voltage or a current? And you'd be surprised that even people who are in the field of electrical engineering or electronics, a lot of them don't really know what it is and say, hey, I got a voltage, or where does voltage come from? What really is a voltage? Now, to be honest with you, this is a topic from chapter 2, and we can actually skip this and go right into the electrical stuff that you're here for. That starts with Ohm's law. What I find is if we do these fundamental, answer the fundamental questions of what are these three quantities, then students tend to understand material later in the course a little better, and you definitely understand material in the next course, which is called AC circuit analysis. So I want to spend some time talking about what is the nature of voltage, what is the nature of current, what do we mean by resistance. So hopefully, if we can get through everything tonight, you'll be able to answer these three questions by the end of the night. If not, it might roll over to the next lecture, but we'll see. So to do this, though, to get at these three questions, we have to back up a little bit and talk about a topic that probably you learned about when you were in grade school or maybe junior high school or high school. We need to talk about the atom. So I want to spend a few minutes talking about the atom. And when we talk about the atom, there's a lot of different models we can use to describe the atom, but there are two main models that's used to describe atom or atomic theory. The first one you're probably familiar with is called the planetary model, or to be more specific, it's called the Bohr model of the atom. The second model, or the second most used model, is called the quantum model of the atom. Now, both models have advantages and disadvantages. The advantage of the Bohr model, or the planetary model, is that it's pretty simple to understand. The disadvantage is it doesn't explain everything about atoms that we might need to know. The advantage of the quantum theory, or the quantum model of the atom, is it explains a whole lot, but the disadvantage is it's kind of hard to grasp. Some of the concepts are really, really abstract. In this course, in order to answer the question, what is voltage, what is current, what is resistance, the Bohr model of the atom works just fine. So if I have any chemists out there, you may be disappointed, but we're going to use a very simple model, the planetary model or the Bohr model of the atom. And this is going to help us to understand the concept of charge, and that'll help us to understand or answer the question, what is voltage and what is current? So that's the goal here. So let me start by just kind of backing up and thinking about, well, what is an atom? And it's interesting because the Greeks, you guys are familiar with the Greek philosophers, Aristotle, Plato, Socrates, those guys. Socrates, I think, was kind of the beginning of, when we think about Greek philosophers, most people think about the Socratics, or people taught by Socrates, and then Socrates had a student named Plato, and Plato had a student named Aristotle, and almost everybody has heard of or know a little bit about Aristotle. But pre-Socratics, those philosophers before Socrates, this is before Christ, they actually deduced or reasoned that there must be some small particle that beyond which you cannot go. It's the smallest piece of stuff that you can have, and they call this particle atome, or atom as we pronounce it today, and the Greek meaning of atom means indivisible. So it's pretty interesting that these ancient Greeks actually deduced, just using the power of their brain, that there must be some small particle, the smallest piece of the thing that you can have. And where they were incorrect is they thought that this thing was a tiny sphere and that you couldn't break it down anymore. So they were right about deducing or reasoning out that there was this thing called an atom, but they were incorrect about thinking that, well, that was the smallest piece of a substance you can have. We now know that the atom itself is composed of particles smaller than the atom. These particles are called subatomic particles, and you know what they are. One is the electron, the other is the proton, and then the third subatomic particle is the neutron. And to go beyond that, we now know that those three subatomic particles are actually made of even smaller particles, which I don't want to go into that. Every time we peel back the layer of an onion, we see that there's something else there, and atomic theory works exactly the same way. So what I want to do here is to just kind of remind you of the atom using the planetary model, and then we're going to use this to explain something called charge. What do we mean by charge? And that's where we start actually understanding voltage and current. So I want to draw the simplest atom that I can draw. The simplest atom I can draw contains a positive charged particle in the middle called the proton, and then going around it, orbiting around it, there is another little spherical object that has a negative charge, and that's called the electron. So the smallest or the most simplest atom I can have, if you had chemistry or some course like that, you will recognize that to be the hydrogen atom. Hydrogen has an atomic number of 1, and the atomic number basically tells me or tells us how many protons the atom has. And since hydrogen has atomic number of 1, it indicates that it has 1 proton. Now, there's 3 subatomic particles. There's the proton, there's the neutrons, and then there's the electrons. And I'm not drawing any neutrons here. As I go through this discussion, you'll never ever see me draw neutrons. I'll never even talk about neutrons, at least not in this class. And the reason is neutrons contribute absolutely nothing to electrical theory. They're not charged particles, so they contribute nothing to electrical theory. Therefore, it doesn't do us any good to talk about. So This model is not complete because I'm not showing the neutrons in the center of the atom. But again, we ignore those because they don't contribute anything to our conversation. So the way to think about this is number one, remember what I'm trying to do here. I'm trying to show you the atom is a three-dimensional object. So I'm trying to show you something that's three-dimensional on the two-dimensional surface. This whiteboard is 2 dimensions. And so what I'm drawing is a circle here. I got the nucleus, which is the proton, as a circle. The electron is a circle. And this little dotted line represents the path the electron is taking as it revolves around the proton, as it revolves around the nucleus. My point is that these are not really circular. These are spherical. So I'm trying to draw something that's 3 dimensions. A sphere in a single dimension is a circle. So remember that this thing is actually, this is a sphere, and then this path, this trajectory that the electron is following as it revolves around the nucleus, as it revolves around the center proton, that is also spherical. And so the electron is moving around that centerpiece, is moving at quite a fast pace, is moving at 186,000, let me write that down. The electron has a velocity of 186,000 miles, not miles per hour, but miles per second, or 3 times 10 to the 8 meters per second. And that 3 times 10 to the 8 meters per second is 300 million meters per second. And that happens to be, in both cases, the speed of light. So electrons actually revolve around the nucleus, revolve around the centerpiece at the speed of light. So literally, they're everywhere at once. The electron is moving so fast, it's everywhere at once. It moves so fast that chemists, they talk about an electron cloud existing around the nucleus of the atom. So that's one thing to observe, is that electron is not stationary, it's actually revolving around the nucleus and is moving at a very, very high velocity. The other thing to note about this model of this simple atom that I have on the board is notice that the centerpiece, which is the proton, I have that drawn bigger than the electron. Now, they're not drawn to scale by any means, but I did exaggerate this because even though I have a single proton here and a single electron there, I drew the proton bigger than the electron because, in fact, the proton is approximately 2,000 times more massive than the electron. The proton in this hydrogen atom is approximately 2,000 times more massive than the electron. Well, why is that important? Well, that's important because what you're going to discover in this discussion is that when we talk about current, what is current? Well, what current really is charge in motion. Current is charge in motion. So if I want to make an electric current, I got to take something that has charge and I got to move it. Well, there's only 2 things in nature that has charge. One is the proton and the other is the electron. And so if I want to make electric current, I got to move either protons or electrons. And since the electron, number one, is about 2,000 times less massive than the proton, it should make sense that it's easier to move something with less mass than it is something with more mass. If I have a bowling ball in this hand and a golf ball in this hand, it's much easier to move the golf ball size particle than it is the bowling ball size particle. And the other thing to note about my picture here is that each one of those subatomic particles, the proton and electron, they have something called charge. They have something called charge. And that's actually vitally important for what we want to talk about and understand in this class. Now, this concept of charge, physicists or scientists really, we don't know what it is. All we know about charge, we know 2 things about charge. We know there's 2 types of it. And so we call one positive charge and one negative charge. And the other thing we know about charge is that it is conserved. Charge is conserved. Now, what does it mean to say something is conserved? Well, in science, if something is conserved, that means it can't be created or destroyed. All you can do is move it around. And most people understand, they could even recite what we call the conservation of energy principle. Energy is neither created or destroyed. You can only change it from one type to another. So most people understand that energy is conserved. But not a lot of people understand that there's other natural quantities that are also conserved, and one of them is charge. Momentum is conserved, charge is conserved, mass is conserved. There's other quantities that's conserved. Well, charge is one of those quantities that's conserved. So we don't make charge, or we don't make charge disappear. All we can do is take charge and move it around to different spots in the universe. Here's the other thing about charge. That's kind of funny. If I have two of the same types of charges, say I got a plus, let me get a prop here. So I got a plus charge and a plus charge. If I try to bring those together, they push apart. If I got a minus charge and a minus charge, if I try to bring those together, they push apart. If I have a plus charge and a minus charge, they come together. Now, you've all experienced something like that because you played around with magnets. Most people have played with magnets. And if you ever played with a magnet before, you know that if I orient two magnets a certain way, they'll push apart. If I flip them both around, they push apart. If I leave one here and move the other one around, they come together. Magnets have what we call them poles. They have magnetic poles, North Pole and the South Pole. And if I have two of the same poles, a north and a north, they repel. A south and a south, they repel. If I have a north and a south, they stick together. Like magnetic poles repel each other, unlike magnetic poles attract each other. Charge behave exactly the same way. If I have two things that have positive charge, they repel each other. If I have two things that have negative charge, they repel each other. But if I have a positive charge and a negative charge, they attract each other. So here I have the nucleus of this hydrogen atom, the proton, has a positive charge. And I have the electron has a negative charge. And even though the proton is 2,000 times more massive than the electron, the charge of both is exactly equal but opposite of the sign. And so there is actually a force of attraction between the electron and, for this case, the nucleus, the proton. There's a force of attraction because unlike charges attract each other. Now, I want you to write something down. I'm going to put the name on the board, but I'm not going to write it out. I want you to write it out because this is really where the study of electronics begins. It's called the law of charge. So you write this down if you're taking notes. The law of charge. I don't know if my purple marker, let me get another purple marker. I don't think this one's working enough for me to be happy about what I'm writing. Get another one here. That was not writing at all. Yeah, there you go. Okay, so the law of charge, I've already stated it. Law of charge. And the law of charge states that like charges repel, unlike charges attract. So write that down. Like charges repel, unlike charges attract. The law of charge. Now, let's continue to talk about this atom. Something else here we can think about. I'm going to draw a square around the atom. I'm going to draw a square. This region right here I'm going to make green. If I ask you how much total charge is in that green area, if I ask how much total charge is in there, how would you answer that? What's the net charge in that box? What's the total amount of total charge in the box? Anybody?
0.
0. Why is it 0? Well, it's 0 because we have exactly the same quantity of charge, but the sign of each is different. I have exactly the same amount of charge. The electron and the proton has exactly the same amount of charge, but the sign of that charge is different. They're opposite. And so I have basically a net charge of 0. But here's what I'm going to do. I'm going to remove this electron. So I got the electron, I'm going to take it out of this region. And remember, charge is conserved. So the electron can't just disappear. All I can do is move it around. So I'm going to move it out of this region right here to over here, somewhere else in the universe. So here's the electron. Now, when I look in the box and I say, all right, what's the net charge in the box? You would answer, how? What is the net charge in the box?
Positive charge.
About plus what? Plus 1. I now have an atom that's charged. I now have an atom that's charged, and that atom has a charge of plus 1. So there's a name for a charged atom. It's called an ion. In this case, I have a positive ion. If I go back, I put the original electron back, I now have a net charge again of 0. And let's say I get another electron from another atom nearby, and I some kind of way force this atom to take on a second electron. So here's my second electron. So I now have 2 minus charges in the box, and I have 1 plus charge in the box. So now I have a charge of a net charge of -1. So again, I have an ion, but this time, instead of charging the ion to be positive, I charge the ion to be negative. I added electrons to a neutral atom. So the term ion, you want to remember that it's just a charged atom. What else can we talk about? There is and I think I put this up on your blackboard. So there's a document that probably you're familiar with already if you had chemistry or some kind of class that involved chemical elements. You dealt with this periodic table. Now, again, I think I put this on Blackboard, but what you want to do is print this out and add this to your class binder, because you get to use this periodic table on exams and quizzes should you need it. Should I ask questions that involve the periodic table? So when I give quizzes and exams, they're closed book, closed notes, no notes allowed, but you are allowed to have this periodic table if you need it for the exam or for a quiz. So I would print that out, have it in your 3-ring binder, be able to access it easily, because if you need it on the exam, you won't be able to look it up on your phone. But just to talk a little bit about the periodic table, just briefly, you'll see that it's arranged in columns and rows. And the main thing I want to point out here is that each element has 2 things. Each element has a symbol. So the symbol for hydrogen is a capital H. If you come all the way over here, helium is a capital H, lowercase e. We can go across each row, and you'll notice these chemical symbols. So certain symbols are important for this class, and I will point them out as we go through the course. So the chemical symbol is important, and also the number. Now, can anybody tell me what this number is? Like hydrogen has a number 1, helium has a number 2, lithium is 3, and so forth. What is this number? What does that number represent? Anybody?
The number of protons?
That's exactly right. So those numbers represent the number of protons. And now it's important that you get this right. Those numbers represent the number of protons. The numbers are called the atomic numbers, and they represent the number of protons. And I emphasize that because students often say, well, that's the number of electrons, and that is not a true statement. What is true is that those numbers represent the number of protons. And if we assume a neutral atom, then we can say that it also represents the number of electrons, if you assume a neutral atom. And in this class, when we do work with the periodic table, we will always assume that we start with a neutral atom when using the periodic table. And I'll demonstrate that tonight. I think that's really all I want to show you on the table for now. But I do want to emphasize, print that out, add it to your binder, you may or may not need that on quizzes or exams. So, let me clean this up a little bit. And I want to go to an atom that has more than a couple of electrons in it. So now I'm going to I'll just draw the nucleus as just sphere. And then I'm going to put these rings around it, which represent, as I said before, the path that electrons take as they revolve around the nucleus. So I'm going to draw these rings. Now these rings actually have different names. They're called energy levels. Sometimes they're called shells. They have different names. I'll use the word energy levels and shells kind of interchangeably. But what I'm trying to draw here, here's the nucleus. This contains the protons and, of course, the neutrons, which we're not talking about. But then these rings represent the path that electrons take. Now, these electrons are actually a certain fixed distance away from the nucleus. And each one of those, I'll call them shells. Each shell can hold a certain number of electrons. Now, what we like to do is we like to name these shells or these rings, the area where the electrons can exist. And remember what I said earlier. I'm drawing circles, but these are really spheres. So you can think of electrons as kind of revolving around the nucleus, but they actually revolve around 3 dimensions. So if you think of a ball encapsulating this, that would be the first shell. And the bigger beach ball encapsulating that would be the second shell, and so forth. Well, these shells, we name them with letters of the alphabet. We name them with letters of the alphabet. So let me just make a space here. We start with K, and we go K through N, and we start with K. K is the closest one to the nucleus. So I'm going to just name these. This is the K shell. This is the L shell, the M shell, all the way out to N. So now, if we label them like that, I can refer to a particular shell. You know exactly where to look. I can say, hey, look at the L shell. You can look at the L shell. So that's important. Now, the thing about shells to understand in the Bohr model that we were talking about, each shell can only hold a certain amount of electrons. Think of a shell like a bucket of different sizes, but instead of holding water, it's a bucket that holds electrons. And so each shell has what we call a shell capacity. A shell capacity. And it's important to be able to determine the shell capacity. And the way you do that is there's a simple equation that you can use for shell capacity. When I talk about shell capacity, I just abbreviate it SC for shell capacity. And the shell capacity is equal to 2n squared, where n is the shell number. So write this little equation down, and then you'll have it, and then I'll show you how to use it. The shell capacity is 2n squared, where n is the shell number. Now the shell number, all we do is we just count these. Starting from the one closer to the nucleus, K is the first one, and then we go 1, 2, 3, 4. So I like to make a little table. Make this little table, and then we'll use that equation to populate the table. What we have is the shell, and that's K through N, K, L, M, N. And then we have the shell number. Let me just use an N, because that's what we had in the equation. So that's that N, that's the shell number. So K has a shell number of 1, this has a shell number of 2, 3, and 4. And then lastly, we got the shell capacity. How many electrons can go into each shell? So that's when we use the equation. So for the K shell, the shell capacity is 2N, I think I used a capital N. The shell capacity is 2N squared, where that N is the shell number. So if I have K as shell number 1, and I got 2 times 1 squared, well, 1 squared is 1, and 2 times 1 is just 2. That means the K shell can hold a maximum of 2 electrons. But go here, the L shell can hold as a shell number of 2. 2 squared is 4, and 2 times 4 is 8. So the L shell can hold 8 electrons. And then M, of course, is 3. So 3 squared is 9, and 2 times 9 is 18. So M can hold a maximum of 18 electrons. And the last one, N, has a shell number of 4. So 4 squared is 16, and 2 times 16 is 32. So the N shell can hold a maximum of 32 electrons. So what happens is, if I have electrons I want to put in the atom, in the shells, I just can't put them anywhere I want. What I got to do is, I got to start with the one closest to the nucleus. I'll put electrons in that shell until it's full, and then I go out to the next one. So let's say I have 3 electrons I want to place in this atom. I got 3 electrons, 1, 2, 3. Well, I got to populate the K shell first, because that's the one closest to the nucleus. So this one right here, we're going to K shell. I'll just make it red. Well, K can hold 2, so that next one can go in the K shell. But once I put that second one in the K shell, now the K shell is full, because it can only hold 2. So that third one I want to place is going to go in the L shell. It's out here somewhere in the L. And now I have all my electrons placed. I don't have anything, if I have 1 in the L, I don't have anything in M and M, because I got to fill up the L shell first before I go out to the next shell, the next level. Now, there's a term I want you to write down, the term valence. The valence. So the valence shell is the last shell that has electrons. So in this case, the way I have the 3 electrons, the valence shell will be the L shell, because it's the last shell that has electrons. If I added 8 to L and I got one more, 9, then that would be, the 9th one would be here in the M shell, and that would be my valence shell. So whatever shell, the outermost shell that has electrons in it, that last shell is called the valence shell. And the electrons in the valence shell, go figure it, they're called valence electrons. So valence electrons are the electrons in the outermost shell. Now that's important for what we're going to do here, because the number of electrons in the outermost shell tells us something about the atom that I'm going to talk about in just a second. I want to make sure everybody's clear on what I did here. Everybody understand this idea of shell letters or labels, shell numbers, and how to use the shell numbers to get the shell capacity. Then once you got the shell capacity, to place those electrons, you always start with the shell closest to the nucleus, place those electrons in that shell until it's full, and then you go out to the next one, place electrons there until that's full, and then you go out to the next one. Anybody have any questions over anything I just showed you or talked about? All right. Well, if you don't have questions, I want to write this down somewhere, because we're going to refer to this in just a second. But I want to move on to another topic. And we'll come back to this table.
So valence shell means the outermost shell.
I'm sorry, say that again.
So valence shells means the outermost shells. That's
correct. The valence shell is the outermost shell that has electrons in it.
Oh, okay.
The outermost shell. I don't know if this is going to be cut off. I think I'm okay. I'm going to abbreviate. This is conductor, and this is semiconductor. I'm not going to write it out, because I think I'm running out of space. And I got one more, insulator. All right. These three terms are extremely important to electronics, and the first one and the last one are very important for this class. The middle one I want to talk about a little bit, but I'm not going to spend a lot of time on it. If you are EET, if that's your major, if you're like electronics, electrical engineering technology, then you will study the middle one in detail at a later class. But I want to talk about, I'll mention all three, but I want to talk about mainly focus on the first one and the last one. So who can tell me what a conductor is? Now, when I say conductor, I mean electrical conductor. These are all, you can put the term electrical in front of all of these. What is a conductor? Electrical conductor, anybody? What is it?
Something that's good at not conducting, but attracting electricity.
Okay. Now, I like the fact that he said not conducting, because he understands that when you define something, you can't use the word in the definition. So he didn't want to say conductor, which was a good thing. So yeah, you're exactly right. Another way to say that is an electrical conductor is something that allows current, electrical current, to flow through it easily with relative ease. So if I have something that's a conductor, current can flow through it easily, and most people understand that most metals are good conductors. We make wires out of metal. Most metals conduct. All metals don't conduct current equally as well, but pretty much compared to other materials, all metals are pretty decent conductors. Whereas an insulator is what?
It resists current.
Yeah, it's kind of like, it doesn't like current to flow through it. So whereas maybe I might have some copper, we know copper is a pretty daggone good conductor. Insulator might be something like rubber or glass or even wood. Those materials don't like to pass electrical current, so it's hard. Somebody said they resist the flow of electrical current. Well, that's exactly right. Now, often we use conductors and insulators together. For instance, if you have a wire, maybe you have a plug, maybe you have a TV or a vacuum cleaner, you plug into the wall. Well, the blades that go into the wall outlet are conductors, and they actually make contact with contacts in the wall outlet, so current can flow into the metal blades. But you handle the rubber part or the plastic part that wraps around the wires for safety. So most of the time we use conductors and insulators together. But conductors allow electricity to flow easily, insulators do not. And so you might just kind of imagine from that the semiconductor is kind of right in between. It's not a good conductor or a good insulator. But semiconductors are extremely important because semiconductors basically pretty much built new technology. You heard of transistors and integrated circuits and all those type of gadgets and devices. Well, semiconductor technology, or those devices are based on semiconductor technology, which is basically based on silicon crystals. And we won't talk a lot about that again. If you're electrical, if you're EET, you'll take the electronics course here at Cincinnati State or at UC if you go to UC. And I don't know if I have any UC students. I usually have one or two every semester here. But you'll take electronics and you'll study semiconductors. Now, I have a diagram I want you to look at. Let me put this on the camera. And I hope this comes up right because it was flipped the wrong way, and I tried to straighten it out. Let me see if it's going to work. Yeah, see how that's flipped? Now, I don't know if I can turn this. Let me see if this has the ability to turn it. I don't think this software, I don't think I can flip this over. I tried to flip this over and save it, flipped over, but I wasn't able to do it. So I apologize. You got to look at it. I guess you got to turn your head sideways and look at it. I don't know. But anybody ever, let me get out of this. Anybody ever seen a graph? Maybe in your math class, they'll have a graph like this. They'll have a graph. And I'll just put X and Y in here, but it could be It could be anything. But sometimes what they'll do is they'll show a little mark right there like this. Anybody ever seen that thing on the graph? I want to know, what is that?
It's a break.
Yeah, what does that break indicate?
It's skipping a certain amount of time or whatever.
Yep. It means there's a skip here, not physically, but what it is, there's actually more data here, but it's so boring that we don't have to draw. There's a long part of the graph that's not shown. And the reason I bring that up is because you go back to this picture. Go back to the picture I just had on there. Let me. Now, guys, you might want to. I don't know how to make this thing turn over, and it's really irritating me. Let me see what this does. This doesn't do anything. You would think they would have. No, I can't. I don't know how to flip it over. But anyway, I brought that up because you see, I'm going to draw it here. They have the same. Right here, they have this, and they have it again on the other side. And what that is they're showing you that on this line, there's actually a long line. They just cut that part out because it's too long to show on the paper. So they're showing you that there's a break there. But what you have here is on one side of this, if you're actually looking at it the right way, like if I rotated it 90 degrees so that this thing is sitting here the right way, what you have here is you have conductors on one side, and then on the left side, you have poor conductors. Now, poor conductor is a good insulator. So on this side I'm circling now, those are insulators, and on the other side, they're conductors. Now you can't see it. Let me erase that line. Let's see how I erase that. But you'll see right here, that's 10 to the, I don't know what that says. I can't, anybody see what that says? 10 to the what? 8th or something? I can't see it. Let me see if I can blow it.
I think it's 10 to the 8th.
For good.
That's 10 to the 8th. That's a 1 with 8 zeros on it. So that number is not going to mean a whole lot right now, but that's called the conductance of it. So the way to think about conductance is if it has a high conductance, that means it has a low resistance. If it has a low resistance, that means it has a high conductance. Right? So they have some examples here. They have gold, they have silver, they have copper, they have aluminum, they have iron. And so these are all very, very, very good conductors. But as I move to the left, or the way this is oriented, as I move down, my conductors become less and less good conductors until I get to the point to where I'm right here. And now, this part, these are semiconductors. They're not really good conductors, but they're not really poor conductors. They're kind of in between. If I keep going, eventually I leave the semiconductor and I get to poor conductors or good insulators. So I got wood. I keep going. Glass is a better insulator than wood, and rubber than glass. And I can keep going. But notice this right here is 10 to the minus 16th. That's the conductivity of it. So I go from 1 with 8 zeros all the way down to 10 to the minus 16th. In other words, the gulf between good conductors and bad conductors is huge. There's a big space between insulators and conductors. So big it's hard to imagine. So what we like to be able to do is, given a certain material, I like to know if it is a good conductor or a bad conductor. And here's how you tell that. Given an element in the periodic table, you can easily tell if that element is going to be a conductor, a semiconductor, or an insulator by, you start with a neutral atom. So we got an atom that has it's a neutral atom. So that means the atomic number tells us the number of protons, but since I have a neutral atom, it also indicates the number of electrons. And what we do is we count the number of valence electrons in that neutral atom. We count the number of valence electrons in the neutral atom. And if the material has 1, 2, or 3 electrons in the valence shell, then that material will be a conductor. If that material has 5, 6, 7, or 8 electrons in the outermost shell, then that material will be an insulator. And if that material or the atom has exactly 4 valence electrons, then that material made out of that element will be a semiconductor. So you want to, given a certain material, you can use the periodic table to figure out if we're going to have a conductor, insulator, or semiconductor, by just counting the number of valence electrons. So what I want to do is let's give this a shot. We'll try it. Now we all know that we all know that copper is a conductor. And even on the diagram I just showed you, one of the metals they had silver, but then right on the other side of silver they had copper, indicating that copper is a good conductor. But I want to use this method to figure out, does it really indicate that copper is a conductor? If it does, then copper should have 1, 2, or 3 electrons in the outermost shell. So how would I start that? I want to know, is copper a conductor, insulator, or semiconductor? And we know the answer. We know, in fact, that it is a conductor. But how would you prove that using this table right here? Well, you start with the periodic table. So get out your periodic table, or I'll bring mine up, and somebody tell me the atomic number for copper. What is the atomic number for copper?
29.
29. And if you wonder, if you know the chemical symbol Cu, if not, you got to read these names here. But copper is right here, and its atomic number is 29, which means it has 29 protons. But since in this class, we always assume we have a neutral atom. If we have 29 protons, then we can assume we're going to have 29 electrons because that atom is neutral. So now I know that copper has an atomic number. I'm going to use Z for the atomic number of 29. Now, if you had chemistry, there's a certain method that chemists use to do what I'm about to do, but I like to just show this with dots. So what I'm going to do is I'm going to represent each electron with a dot. And I'm going to show 29 of them. What I like to do is just group them in groups of 10s. So these are the 29 electrons that copper has right here. I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. So there they are. And what you'll do is we'll start to put these electrons in the shells over here. But you got to remember 2 things. Number 1, each shell can only hold a certain amount. So when a certain shell gets full, I got to go to the next shell. So I got to know the shell capacity. And then the other thing to remember is when I fill these shells up, I start with the one closest to the nucleus first and work my way out. So these 2 electrons right here are in the K shell. This K can hold 2. How many can L hold? What's the maximum number of electrons the L shell can hold?
8.
It can hold 8. What about the M shell? How many can the M shell hold? The max?
18.
18. So I have 10 here. I have 9 here. 18 of those are on the M shell. That means that that electron right there is in the end shell. And since that's the outermost shell, then that would be the valence electron. And there's one of them. Well, if an atom has one electron in the outermost shell, it's a conductor. So I can use this to predict, given the atomic number, I can tell right away if I'm dealing with a conductor, an insulator, or a semiconductor. So I think this problem using copper was actually on, I have a practice sheet on Blackboard. I think this was actually on the practice sheet. So you want to be able to do something like this for a quiz or exam for me. Be able to, given the atomic number, tell me if the material is a conductor, semiconductor, or insulator. And let me say one more thing about this before I move away from it. On the other end over here, the insulator. The more electrons the insulator has in the outermost shell, the better insulator it is. So the best insulators will have 8 electrons in the outer shell. That's called a full shell. And I think it's been a long time since I had chemistry. I graduated from college in 1996. Some of you weren't even born in 96. But I think they call that an octet. Octet. When there's 8 electrons in the outermost shell, we say that the atom is stable. Now, what does it mean to be stable? That means it's chemically stable and electrically stable. Chemically stable, it won't interact with other chemicals or other elements really well. For us in here, it means that it's really, really hard to rip that electron away from the atom. So those elements that are insulators that are composed of elements that have a full shell, a full 8, they're really, really, really good insulators. So if you're ever doing any kind of work and your boss says, hey, we need a good insulator for this project, when I say insulator, I mean electrical insulator. Well, you understand a little bit more about the full shell. The fuller the shell, closer to 8. We don't know what's special about the number 8, but we just know this. In nature wants 8 in the outermost shell. Scientists call that the magic number. Magic number. 8 is the magic number. When the atom has 8 valence electrons, it's really stable. All right. Well, I'm looking at the topic sheet, and we've talked about number 1, which is atoms, the Bohr model, energy level or shells, valence electrons, and ionization or ions. So we talked about that. And then the second thing to talk about is categories of materials, electrical categories. Well, that's the semiconductor, the insulator, and the conductor. We talked about those. And then the third thing would be to talk about, it says electron structure here, but I mean shell capacity. And how will you use shell capacity to figure out if I have conductors, semiconductors, or insulator? And I just kind of showed you an example of that. So again, I think on the practice sheet, I think you'll find that one that we had using copper, I think that was one of the very first problems in the practice sheet. So let me pause here for a second to see if anyone has any questions over anything I talked about so far. Any questions? Okay, well, let's pause, take a little break. Normally, if we meet face-to-face, every hour I'll give you like a 10-minute break, and we don't have to break for 10 minutes, but I want to take a break for a few minutes. I'm talking, when I talk for an hour, sometimes I gotta just take a little breather. So I want to break for about 5 minutes. We'll just pause for about 5 minutes. If you need to go away from the camera, come back in about 5 minutes, and then we'll start. And the next thing I want to do is talk about something called electrostatics. And then that'll help us to understand the concept of voltage. So see you in about 5 minutes. So I want to talk about charge. I've already mentioned that term today. We know charge, what we know about charge is there's two types, plus charge and minus charge. We know that the origin of any positive charge would be ultimately the proton, and the origin of any negative charge ultimately would be the electron. But let's talk about charge a little bit more. Now, charge is one of those words that can be used as a noun or a verb. There's certain words in the English language that can be used as both a noun and a verb depending on how you use it. Remember, a noun is a person, place, or thing. A verb is some kind of action word. So one example of that would be, let me see, Google. Google's the name of a search engine, so it's a noun. It names something. But I can also tell you to go Google something, and now that's an action word. You got to go do something. So you can probably think of many other words that can be used as a noun or a verb, and charge is one of those words that can be used as a noun or a verb. When I use charge as a noun, it's the name of the type of charge that either is possessed by an electron or proton. So something can have charge. We know protons have positive charge. Electrons have negative charge. So that's one way to use the term charge. I'm going to use it not as a noun. I want to use charge as a verb. What does it mean to charge something? So let's look at that. Let's answer that question. Now, I've actually already showed this example, but I want to show it again. Let's say I have let's say I have an atom that has the atomic number 4. So we know that there's 4 positive charges in the nucleus. And actually, let me just do 2. Let's do 2. Doesn't really matter, but I don't have to draw all those rings. So let's say we have atomic number 2. So that means there's 2 positive charges, 2 protons in the nucleus. And then if I have a neutral atom, it's going to have 2 electrons. So here's 1 electron. Here's the other electron. And what I'm going to do is exactly what I did before. I'm going to enclose this atom in a region. We'll make it rectangular, but it doesn't have to be rectangular. So I got this region. Say I put it in a box. Take that atom and put it in the box. Right now, if I ask about charge in the box, of course, you're going to tell me then that charge is 0. There's no charge in there because I have the same number of positive charges and negative charges. Well, I want to charge the atom. I want to charge it up. I want to charge it. So how do I charge it? Well, one way to do it would be to reach in here and take this electron out and put it somewhere else in the universe. So I'm going to stick this electron right here. And now when I come over to the box and I look at it, I have 2 positive charges. I only have 1 negative charge. So now the net charge in this box is positive 1. I have charged the region inside the green box. I charged it. Well, let's go back to the original picture, where I have 2 protons, and I put this electron back in the box, and now I'm back to a situation to where I have no charge in the box. I have things that have charge in the box, but the total charge in the box is 0 because I have the same number of positive and negative charges. So the net charge in the box is 0. Now I'm going to reach somewhere else in the universe and find another electron. I'm going to put that electron in the box. I'm going to stick that 3rd electron in the box somewhere. And now when I say, all right, how much charge is in the box? You're going to say, well, I got 2 positive charges, but I have 1, 2, 3 negative charges. So now, again, I've charged the atom, but this time it's a -1. So the first time I charged the atom, it had a positive charge on the +1. The second time I charged the atom, it had a -1 charge. It was 1 additional electron. In both cases, what did I have to do to charge the atom? Anybody? What did I?
Add or remove a electron.
Okay, we had to add or remove electrons. Add or remove electrons. And in this class, when we talk about charging something, that's exactly what we mean. In order to charge anything, this is what you want to write down. In order to charge anything, there must be a transfer of electrons from one place to another. So when you use the word charging, that's what you mean. Example, your cell phone dies and I want to charge my cell phone. So you plug in the charger, plug the charger into the phone. There must be a transfer of electrons from the phone charger to your phone. I go outside, I left my headlights on, my car battery is dead. Let me get a jump, I need to charge my car battery. When you charge your battery, you're transferring electrons from one battery or battery charger to the dead battery. There must be a transfer of electrons. Anytime you charge anything, you use the term charge in this class, that's what you're talking about. You're using the term charge as a verb, and to charge anything, there must be a transfer of electrons. So let that sink in, because now that you heard that, when someone uses the term charge, hey, I got to go charge my cell phone, since you have engineering background, engineering technology, you now know that they mean we got to move electrons either into something or out of something. Charging means you have to take electrons and move them from one place to another. Questions or comments? Okay. So I'm looking at the topic sheet again, and I'm looking at Roman numeral 4, and it talks about electrostatics, the term electrostatics. And then there's a question in italics. It says, what is happening physically when an object is charged? And the answer to that is, what is happening physically when an object is being charged is that electrons are being moved from one place to another. If I'm charging anything, there must be a transfer of electrons from one place to another, or from one thing to another, one device to another. There must be a movement or transfer of electrons. And the term electrostatic, well, the word electro means it has to do with charge, and statics means that there's nothing moving. So there's no charge moving. When we get down to like Roman numeral, 4, 5, 6, electrodynamics, the word dynamic means now the charge is moving. So now we're talking about current flow. But right now at Roman numeral 4, we're talking about electrostatics. Charge that's stationary. So what you now know is that in order to charge any object, anything, there must be a transfer of electrons. Electrons have to move. If nothing moves, nothing is charged. So let's dig into this idea of charge. Now in science, we use in science and engineering, we use numbers to represent size or amount. And then we use letters to represent quantities or units. Okay, so I want to make sure you understand what I mean here. Of course, we use numbers to represent the amount of something, but we use letters. A letter can represent a unit, or it can represent a unit, or it can represent a quantity. So an example of that would be, in this class, we're going to use, for the quantity called current, we're going to use the letter I for a quantity called current, but the unit for current is the ampere. So we're going to use the letter A to represent the unit. So this represents the current quantity, and this represents the unit. So what I like to do, so you know which one of these is the quantity, which is the unit. If I have a unit, I like to show it in brackets. So now you know that this represents a quantity, and this represents a unit. We'll do the same thing for resistance. We'll use a R to represent the quantity of resistance, but we'll use this Greek omega sign to represent the unit of resistance. So I put a bracket around there, and you now know that that's a unit. We do the same exact thing for charge. For charge. So charge the letter we use to represent charge is Q. And Q stands for quantity of charge. So instead of writing it out, quantity of charge, let's use Q, quantity of charge. The unit for charge is called a coulomb, capital C. So the unit for this symbol right here is capital C. We'll put brackets around that so you know that that's the unit. And that unit C stands for coulomb. It's a capital C. I don't know if you remember, but I mentioned that if you have a unit that has a capital letter, then it's named after a person. So the Coulomb symbol is a capital C. Then after Coulomb, I can't remember the physicist's first name, but I think it's Charles Coulomb, if I'm not mistaken. So we use the letter Q to represent charge. C is the unit of charge. And then we talk about what a coulomb is, because a coulomb of charge is an amount of charge. A coulomb of charge is an amount of charge. So I want you to think of charge. We package charge up in certain sizes, and you do that all the time, right? Like when you go to Kroger's and you buy eggs, you don't go buy one egg. You don't buy 3 eggs. You buy a dozen of eggs. When they package eggs, they package them by the dozen. I don't know how many cigarettes are in the pack. Anybody smoke cigarettes? How many cigarettes come in the pack? Anybody?
20.
20. So when they package cigarettes, 20 cigarettes equals 1 pack. So 12 eggs is a dozen. 20 cigarettes is a pack. If you have 6.25 times 10 to the 18th electrons, then you have 1 coulomb of electrons. So 20 cigarettes, 1 pack, 12 eggs, 1 dozen, 6.25 times 10 to the 18th electrons, 1 coulomb. So if they sold electrons at the store, you would go buy this many of them. They sell them in the packages. Not just they can exist in any amount, but when we think about them, we group them in coulombs. So quantity of charge Q, the unit is coulombs, and 1 coulomb is equal to this many electrons. Now, you got to be careful because, let me see if I can explain this, if you can follow this. Let's say I have, here's a bunch of positive and negative charges. So right now I got the same number of plus and minus charges. So that means that the net charge in here, is 0. So Q is charged. The net charge is 0 because I have the same number of plus and minus charges. But what I'm going to do is, if the net charge is 0, I'm going to reach in here and grab a bunch of electrons. I'm going to grab 2 coulombs of electrons and put them over here. So here they are. I got 2 coulombs of electrons. So now this charge right here, that's all negative. I started with neutral charge, and I took away 2 coulombs of electrons and put them over here. Now, how many electrons is that? Well, 1 coulomb is 6.25 times 10 to the 18th electrons. 2 coulombs would be twice that, 12.5 times 10 to the 18th electrons. So I reach here, I grab that, I grab 2 coulombs of electrons, put them over here, and now I have a minus 2 coulombs here, because those electrons all have negative charge. But what do I have over here?
+2.
I got a positive 2 coulombs. Because I started off with neutral charge, so I had the same number of plus and minus. I removed some electrons and put them over here. If I remove 2 coulombs, that means I have positive 2 coulombs over here. I did 2 things here. I charged both this region and I charged this region. And remember what I said about charge? In order to charge anything, you got to move electrons. Now, hold on a second, Singleton. Why electrons? Why not move protons? Go back to the atom. Remember the structure of the atom. The middle of the atom has these positive charges. So maybe this is +1, that's +1, that's +1, that's +1. That makes up the nucleus. And then going around the nucleus, you got the electrons. And they have negative charge. Remember at the beginning of this lecture, I said that number 1, the proton is 2,000 times more massive than the electron. Imagine something that is 1 pound. If the electron was 1 pound, that means the proton would be 2,000 pounds. That's a big difference. So it's easier to move something that's 1 than it is 2,000. So this is much easier to move than the proton. But beyond that, look at where the proton is located. The proton is located in the nucleus. It's not free to move. If you reach in there and you were to break that apart, well, that's not a good thing to do, because then you get this big mushroom cloud and everything just goes to hell. You don't want to try to break the nucleus apart. Atomic bombs are based on that idea. So when we move charge, the thing that we typically move is, we could move, in theory, we can move either positive charge or negative. It doesn't matter. But to be practical, you can't move the proton because it's stuck in the nucleus. So the only thing you can move is the electron. So if I start with a neutral condition, I can take the electrons away. The thing I took it away from is positive. The thing I took this to is negative. Or I can add electrons to a situation. But in either case, to charge something to be positive or negative, the thing I'm moving is electrons. In order to charge anything, there must be a transfer of electrons, not protons, electrons. So, I don't know if you guys have that topic sheet. Let me see if I have it. If you got that topic sheet, take it out. I think, I don't have it in front of me, but I think there's some practice problems on there. Take out your topic sheet. I have my topic sheet, but I think somebody, I came in the room, somebody had messed with my papers, and I think they probably, I ain't gonna say they took it, but I'm not seeing it here. But if you have access to the topic sheet, go ahead and bring it out, bring it up. Let me see if I put it online here. Might have put it online. This is the sheet I'm talking about. So here's your practice problems. Now, this first one we already did. We did that one already. So I'm looking at number 2. And look at number 2. It says you have a, here's an interesting word, you have a neutral dielectric, has added to it 12.5 times 10 to the 18th electrons. What's the charge in coulombs? So if I were actually reading this and studying this, that term, I know what the word neutral is. You might not know what the dielectric is. So you would stop, and in my case, I would look it up in the dictionary. In your case, you would probably use Google. I'm old school. So, but it turns out a dielectric, all a dielectric is an insulator. So what this is saying is you have a neutral insulator. It's neutral. And you're going to add to this neutral insulator, you're going to add 12.5 times 10 to the 18th electrons. They want to know what is the charge in coulombs, and that's the charge on this insulator that was neutral. So what I want you to do is get out a sheet of paper. Don't do it in your head, even if you can. I want you to actually write it out. I want to show you how I write this type of a problem out. Write it out and then solve it. So basically, I got 12.5 times 10 to the 18 electrons. And when I add that to a neutral dielectric, and I want to know how many coulombs is that? How many coulombs?
2 coulombs.
Okay, I think that's correct. So we convert this to charge. Now the way I do this is I know that 1 coulomb is the same as 6.25 times 10 to the 18 electrons. Well, in chemistry, they teach you how to use what they call conversion factors. It's like 1 foot is 12 inches, or 3 feet is a yard. 1 coulomb is 6.25 times 10 to the 18 electrons. That's what they call a conversion factor. And so you can set this up where you multiply by either 1 coulomb is the same as 6.25 times 10 to the 18th electrons, or you do it the other way. And you know which one to multiply by because you got to be able to cancel this unit with that one. But there's no way I can cancel the unit of electrons with the C. That means I got this turned the wrong way. I got to flip it over. I got to put this on the bottom and the coulomb on the top. If I flip that over, I know that 1 coulomb is the same as 6.25 times 10 to the 18th electrons. And now things cancel out because I got it in there the right way. The unit of electron cancels. The 10 to the 18th and that 10 to the 18th will cancel. So all I'm really doing is I'm taking 12.5, dividing by 6.25. So whoever said 2 coulombs, the answer is 2 coulombs. Now, you got to be careful because the math doesn't tell you which sign to add. Are these coulombs positive or negative? Which one is it?
Negative.
It's negative. Now, how do we know they're negative?
Electrons were added to the dielectric.
Yeah, and electrons have negative charge. Now, this is an important concept, guys. You got to know when you're doing a problem like this, you got to know if we're dealing with things that are positive or negative. The only reason this worked out is because we started with a neutral dielectric. But let's say the dielectric wasn't neutral. Let's say that let's say this is my dielectric. And let's say that the dielectric had a charge of 7 coulombs. If you don't write whether that's a positive 7 or negative 7, then you really can't answer the question. Because if this is a negative 7, and I add 2 more coulombs to it, well, if you said, all right, if you didn't write that as a negative 2, and you say, all right, I have negative 7 coulombs, and I'm adding 2 more coulombs, well, it looks like negative 5 coulombs, which is the wrong answer, because you added negative 7 to it, or negative 2 to it. So I really have a negative 2, a 7, 8, that's negative 9 coulombs total. I'm not trying to confuse you, I'm just saying, if the starting point, you start with something neutral, then, all right, you can get away with not putting that sign there. But if the thing you're adding electrons to or taking electrons away from, if that thing already has a charge of something, or the thing you're adding has a charge of something, you got to take that into account. So if I have electrons, the electrons are always negative, so the charge produced by electrons, the 2 coulombs, by definition, is negative. The math doesn't supply the negative sign. You have to supply that yourself if you're dealing with electrons. So hopefully that's clear. All right, I think there's another practice problem on there, though. Do the next one. There's one more where you're going the other way. I'll put this back up in case you don't have the sheet. Go ahead and do number 3. You have 3 coulombs, and they want to know how many electrons does that represent? 3 coulombs, how many electrons does that represent? And that was that.
18.75 in times 10 to the power 18 electron.
Okay. So when I'm doing electron, I just put the pound sign for number and a little e for electrons. That's my symbol for electrons. So I got 3 coulombs of charge. I want to go from coulombs to electrons, but I know that 1 coulomb is equal to 6.25 times 10 to the 18th electrons. And if I do it that way, so that whatever unit is here is on the bottom of my conversion factor, and just like before, this will cancel out, and I'm left with electrons, which is what I want. So somebody said if I take 3 times 6.25, I end up with 18.75 times 10 to the 18th electrons, and that would be my answer. So, pretty cool stuff. We can calculate the number of electrons if I know the amount of charge, or if I know the number of electrons, I can calculate the amount of charge. And we learned that in order to charge anything, it must be a transfer of electrons. So going back to the topic sheet, Roman numeral 4, we talked about definition of electrostatics. What is happening physically when I charge an object? If I charge anything, a cell phone, a car battery, anything, there must be some kind of transfer of electrons. The meaning of charging means there's a transfer of electrons. We define the unit of charge, which is the coulomb. We know that is a certain number of electrons gives you 1 coulomb. 6.25 times 10 to the 18th electrons give you 1 coulomb. We know that there's 2 types of charge. Beginning of this lecture, we talked about positive and negative charge. There's 2 types of charge. And we've also talked about the law of charge. The law of charge, I told you to write that down. The law of charge, like charges repel, unlike charges attract. So that leaves us with D, E, and F. 3 different ways to charge something up. So let me just briefly go through that, and then we'll move on to voltage. 3 ways to charge something. These are not in any particular order. I can charge by friction. I can charge by contact. And then there's some called induction. Friction, contact, and induction. So to explain these, I just want to give 3 really simple kind of examples. Well, everybody kind of knows what we mean by friction. In order to have friction, I have things rub together. You know, friction creates heat. But friction can also, you can actually rub electrons off of one thing onto something else. Now, I don't have any hair anymore, but when I was younger and I had a big old afro, I could take a balloon. You ever take a balloon and rub it on your hair? And you can stick it on the wall? Why does it stick to the wall? When you charge the balloon, there was a transfer of electrons, and it actually produces a difference in charge between the balloon and the thing that the balloon is going to connect to. And so you charge that way, and you're able to get the balloon to stick to the wall. If you ever go to the dryer, maybe on a dry day, you put clothes in the dryer. If you turn the lights off, sometimes you pull the clothes apart real fast. If your lights are off, you can actually see artificial lightning or sparks created. The same thing happens on the dry day when if you have on rubber shoes. And the room I'm in right now has carpet on it, and I can drag my shoes across the carpet. I'm basically charging my body up. I'm transferring electrons from the carpet to me by friction. The actual rubbing of my shoes across the carpet moves electrons from the carpet to my body. There's a buildup of electrons on me. If I go over and touch somebody, you might feel a shock or a spark. That's actually demonstrating two of these. There's a transfer of electrons from friction and a transfer of electrons from contact. I'm rubbing my feet on the carpet right now, so friction forces between the carpet and my shoes cause a transfer of electrons from the carpet to my body. I reach over and I touch a person. I don't have to rub them. I just make contact with them with my finger. Now, since there's a buildup of charge on me, that charge wants to go from where there's a lot of charge to where there's no or less charge. If the person I'm sitting next to that I touch, if they have no or less charge on them, neutral charge or less charge, the charge is going to go from me to them. And the spark that you see, you don't see electricity. You see the path it's actually air that's basically on fire. You see the spark or arc that you see is the path that the electrons take moving from one point to another. So my gym shoes on the carpet, charging by friction. Me touching the person on the shoulder, seeing a little spark, feeling a little spark, transfer by contact. So I can transfer electrons or charge by friction, and I can charge by contact. And then this was kind of hard to explain. I'm going to try to explain it. This idea of induction, and I actually kind of have to tell a story to explain this idea of charging something by induction. So what I want you to do is imagine I have a metal ball, a sphere, hanging from a light thread. So here's the ceiling. I got the light thread, and I got this metal sphere, metal ball. And the metal ball has a net charge of 0. If it has a net charge of 0, that doesn't mean it doesn't have any charge on it. It just means it has the same number of positive and negative charges. So let's say I have this many positive charges. If I have a net charge of 0, that means I have this many negative charges. Now I'm not going to have 4. I might have 40 trillion, but I can't draw 40 trillion. So I'm showing 4 positive charges, 4 negative charges. The point is the net charge on that sphere, that metal ball, is 0. So now what I'm going to do is get a piece of glass and some silk. I'm going to rub the silk on the glass. When I rub the silk on the glass, what happens is, just like when I rub my feet or my shoes against the carpet, there's a transfer of electrons from the carpet to me. If I move the silk on the glass rod, there's a transfer of electrons from the silk to the glass rod. So I charge the glass rod. And once I charge the glass rod, what I'm going to do is I'm going to put the glass rod near the sphere. I'm not going to touch it. I'm just going to put it near the sphere. But before I do that, I'm going to do this. I'm going to attach a wire to this ball. Attach it. Well, actually, let me do this first. This will make more sense. I'm going to take the glass rod and put it right here. Again, I'm not going to touch it, but I got a bunch of negative charge from the rubbing the glass rod with the silk, so I got a bunch of negative charge on that glass rod. And since light charges repel, and since this is metal, in metal, those electrons are free to move. It's a conductor, so they're free to move. So if I put this glass rod near the metal ball, light charges repel, unlike charges attract. So what's going to happen is the light charge is going to move away from the metal rod. It's going to move to this side. And the positive charge is going to want to be attracted to the metal rod. So it's going to move close to the metal, I'm calling the metal rod, I mean the glass rod. So all I'm doing is using that charged glass rod to separate charge. Now, while I have that glass rod there, I then take a wire. And this wire now, this symbol right here, I don't know if you've seen this symbol before. Anybody know what that means? Anybody ever seen that symbol before?
Yes, it's ground.
That's correct, ground. Now, we actually do a whole lab on ground because it's not a simple thing. Electrical ground, there's a lot of meanings to that term. And when we in the lab, I go over all of that. But here's one thing to know, just in short, electricity wants to go to ground. Electricity wants to flow to ground. So what I'm going to do is I'm going to attach a wire from here to ground. And when I do that, these electrons now have a path off of the sphere, off the metal ball. They can now flow off the ground. So what's going to happen is these are going to flow to ground, and then I can disconnect that. And now all I have left there are positive charges. So now when I move this away, I've charged that metal sphere to be positive because I've removed electrons from it. Now that's kind of a long story, but that's called charging by induction, the term induction. You might see the term induce in it. So you induce something to happen. You induce the charges to flow off, to flow away, and the result is you end up with positive charges. Now, if I ask about that one on the quiz, I don't even know how you would explain that because that's kind of a long story. I guess you can try to draw this picture and put some words around it to know that you at least heard the lecture, and maybe I'll assume that you understand it or something, maybe try to explain it. But I may not ask for examples, but you should know 3 basic ways to charge something: friction, contact, induction. Friction, contact, induction. Anybody have any questions over charge or charging an object or anything I talked about so far? Any questions or comments?
So when we talk about charge, it means like negative Coulomb. Like in problem number 2, if we said like how many charges in coulombs means like always it is negative coulombs.
It's negative coulombs if we have an excess of electrons.
Okay.
If positive, it's positive coulombs if I have less electrons than positive charges.
So
if I start with something neutral, I'll just draw this little blob. If I start with something neutral, so that means the charge is 0. Now remember, 0 charge doesn't mean there's no charge on it. 0 charge just means there's the same amount of plus and minus charge. If I remove electrons from here, I remove 3 coulombs from here. I remove 3 coulombs of electrons. That would be 3 times 6.25 times 10 to the 18th electron. That's how many electrons I remove. That means I remove negative 3 coulombs. What that means, what's left over here, since in the beginning it was neutral, what's left over here is positive 3 coulombs. So I got to look at what I'm doing. If I'm talking about the charge of the, how much charge did I remove? I removed negative 3 coulombs. How much charge is left? There's positive 3 left on the thing that I took the electrons away from. But if this was already positive 7 coulombs, say you walked in the room and that was already positive 7 coulombs, then you took another 3 coulombs away. You took another 3 coulombs of electrons away. If I take another 3 coulombs of electrons away, the other 3 coulombs are over here, they're negative, but now this is what? Positive 10 coulombs. If I take another 3 away, this will be positive 13 coulombs. So it's kind of a tricky question. If you're asking about what's the charge on the thing that I took the electrons away from, well, if I started with something neutral, I'm like digging a hole. It's gonna be more and more and more positive charge left. If I keep taking electrons away, if I keep adding electrons to it, then I get more and more negative charge. So hopefully that's clear. I don't know if it is or it isn't, but I really, I think it's something you just kind of got to think about, and it should make sense to you. If not, you have to ask me questions.
Oh, yeah. So if I added electrons, so if we add 3 electrons to positive 10, we will get 7 coulomb in it, right?
Yes.
Yeah.
Yeah,
So,
that's right.
so from taking away electrons means like more positive, and then if we add electrons, we get less positive, like that.
That's exactly right.
Yes.
That's right. But the thing to remember, I mean, you can get lost in the details, but it's really the thing to remember is whether I have positive charge here or negative charge, what am I doing to get that charge? I'm moving electrons either away from something or to something. So don't get lost in the detail. The takeaway is if I want to charge anything, I gotta move electrons around. That's all I want you to take from this. The math, we can get into the math and the details of it.
Oh,
But the concept is simple, right?
yeah.
If you want to charge your cell phone, what are you doing? You're moving electrons from the wall outlet to your cell phone. If you want to charge your car battery, you're moving electrons from either the good battery or the battery charger or the jump box to the dead battery. If you charge anything, what you mean by charge, you're moving electrons from one place to another.
Oh, yes.
It must be a transfer of electrons.
Yes, I got it.
All right, well, guys, I know it's too early for another break, but I got to talk about voltage, and that takes a while. And it's maybe, I don't know, 6 minutes before 8 o'clock. So I'm going to pause again for about 5 minutes and then come back. I think current is pretty easy to talk about. Resistance is pretty easy to talk, but voltage takes a minute. So let's take another little break for about 5 minutes or so, and we'll come back. And then I think once we're over the hump once we get through voltage. The rest is a piece of cake, but voltage takes a little bit to talk about. So take a break for about 5 minutes. I'm going to walk away from the camera for about 5 minutes, get some more water, and we'll come in and we'll talk about voltage. Okay, guys, we are back, and we're going to talk about voltage now. All right. So I have these three terms on the board: energy, work, force. What is energy? What is energy? What do we mean when we talk about energy? You guys are sitting there quiet. Don't Google it or anything. Just when you think about energy, how would you explain or define energy? What is it?
I think about energy as being like the food or gas of something. Like what fuels it and what makes it go forward.
Okay. All right. Usually when we use terms like, and I like to ask students, when you think about certain things, what comes to mind? Like electricity, I always think of lightning for some reason. So there's this thought about energy. What about anybody else have any other thoughts? What do you think of when you think about energy? What comes to mind?
It's what allows you to do work.
Okay. And that is actually a standard definition. And that's the one I want to use. Because to be honest with you, energy is very hard to define. So a lot of scientists will define it as the ability to do work. And that's what we'll do. Let's define energy as the ability to do this, work. Now, does anybody know the unit for energy? Anybody have a physics or chemistry class? What's the unit for energy?
Joule?
The joule.
Yeah.
The joule. So the unit for energy is the joule. Capital J is the unit. And it's spelled joule. Okay. That wasn't too bad. Energy is the ability to do work. But now work is also one of the words I want to define. What's work? What do you mean by work? Energy is the ability to do work, but what is work?
That's something you have completed.
Something you have completed. Sometimes people think of work. I'm at work right now. It took me long to get back to the camera because I had to go. My mom sent me a message to call her right away. And she was talking to me, and I said, Mom, I have to get back to work. So, but to an engineer or to a scientist, this idea of work has a very specific meaning. For example, let's say I have a bowling ball, really heavy ball, and I hold it out like this for a long time. If I ask the person holding the bowling, maybe I got a 14-pound bowling ball, and I got to stand here and hold this. If I ask that person holding that bowling ball, are you doing a lot of work? They're going to be like, yep, I'm doing a lot of work. This ball is heavy. But if you ask an engineer or a scientist, is that person doing work? Guess what the answer will be? What do you think?
Is it the amount of energy exerted to perform the action?
Okay, let's examine what you just said. He said the amount of energy exerted, I like that word, and he also used the word to perform an action, exertion and action. So in other words, when you talk about an action, something has to happen. And what has to happen is something has to move. In order for work to be done, something has to move. So the guy holding the 14-pound bowling ball, he's holding that bowling ball for a long time. The bowling ball is really heavy. In his mind, he's doing a lot of work, but if you ask the scientists or engineers, is that person doing work? They'll say no, because nothing's moving. In order for work to happen, there must be force, and that force has to act on the object through a distance. Let me say that a second time. In order for work to happen, for work to be done, I have to have a force, and that force has to act on the object through a distance. Something's got to move. If nothing moves, there's no work done. So work is what happens when a force acts on an object through a distance. And yes, I do know I spelled through the wrong way, but I'm trying to shorten things here. Okay, so look at what we're doing here. We started off talking about energy. Energy is the ability to do work. And then we said, all right, well, what's work? Well, work is what happens when a force acts through a distance. Now, does anybody know, maybe you had physics or chemistry before, does anybody know the units for work? What physical unit do they use for work? Let me tell you, because this is pretty interesting. The unit for work is a joule. This is the only time in physics where you have two different quantities have exactly the same unit. Work and energy are so closely related that they give them the same unit. Matter of fact, I remember when I was in college, my physics teacher told me, he said, Singleton, energy and work are just two sides of the same coin. He said, if I have it as energy, if I give it to you, I remember him doing this. He had the physics book in his hand. He said, if I have it as energy, if I give it to you, he did the book like this, a force acting through a distance, it's work. Well, this is getting deep now. Let's keep on going. So, energy is the ability to do work. Work is what happens when a force acts on an object through a distance. See how these are linked together? Now I'm going to ask you, what's a force? What is a force? What's a force? Now, there's a real physics way to explain what a force is. I know what that is, but I don't want a big, high-powered definition. I want the simplest. If a little kid came up to you and said, "What's a force?" How would you explain to that kid in the simplest way what a force is? What is a force?
Something that make you to walk.
Something they use to walk. Okay. I think that's a good definition. Anybody else have anything else? Well, here's one that I think about a lot. Was somebody going to say something?
It's like an interaction between two things.
Okay. All right. So an interaction between two things. I think that's a good way to think about it. Here's another really simple way, though. A force is a push or a what? A force is a push or a pull. I think that's a simple way to explain it. A force is a push or pull. Now I want to drill down into this a little bit more though, forces, because forces are pretty interesting. There's two things about forces I want to talk about. First of all, somebody in the definition said force is some kind of interaction between things, between two things. Now, the one scientist that did a lot of work on forces is this guy named Newton, Sir Isaac Newton. He was responsible for a lot of things, but he gave us these laws of motion. But one of his laws of motion is just like these laws, Newton's first law, Newton's second law, but Newton's third law deals with forces, and it goes something like this. When people state it, they usually say it the wrong way. What they say is for every action, there's an equal and opposite reaction, but that's not what Newton said. What he really said was for every action force, there's an equal and opposite reaction force. Newton's third law. For every action force, there's an equal and opposite reaction force. And what he was saying was, it's impossible to have just one force. Forces always exist in pairs. It's impossible to have one force. Forces always exist in in pairs. There's the action force and the reaction force. So an example would be this. Let's say I push on the board. I'm pushing on the board. What Newton would say is the board pushing back. Let's say I push on the board. I push into the board with 10 pounds of force. Newton would say, well, the board's pushing back with 10 pounds of force. If you think about it, he has to be correct, because if I was pushing in this way with 10 pounds of force, but the board was only pushing back with 7, that means I would fly through the board, right, with 3 pounds of force. Or if I reverse the situation, if I was pushing this way with 10 pounds, with 7 pounds of force, and the board was pushing back with 10 pounds of force, I would go flying towards the camera. But the fact that I'm pushing really hard on the board, and the board's not moving, and I'm not moving, means that whatever force I'm applying to the board has to apply back because nothing's moving. So forces always exist in pairs. That's the first thing that's interesting. But here's something else that's even more interesting. There's actually 2 classes of forces. There's 2 classes of forces. So the first class of forces is called a contact force. A contact force. So contact forces are really common. I just showed you one. If I put my hand on the board is in contact with my hand. There's 2 forces, right? Newton says there's 2 forces. There's the force of my hand on the board. That's one force. And then there's the force of the board on my hand. That's the second force. 2 forces. So in order to have that, I got one object touching another. So contact forces where there's an exchange or some interaction between things, but they have to make physical contact. But the other class of force is even more interesting. It's called an action at a distance. So I got contact forces, and then I have this other class of forces called action at a distance forces. Now those are cool. What is an action at a distance force? Well, it would work like this. Imagine, well, you really can't see in the camera. I need a prop. I need something to, well, I'll just have to use the marker. So I got the marker in my hand, and I put my finger on the marker. If I apply a force to the marker, then I can move the marker. There's a force of my finger on the marker causes the marker to move. But imagine I just did like this. I never touched the marker. I just got close to it. In some kind of way, the force went from my finger over to the marker and caused it to move. The 2 objects never have to touch each other. Is there really such a force like that, where I have one object exert a force on another object, but yet the 2 objects have to never touch? Are there any kind of forces like that?
Magnet.
Yeah, give me an example.
Like the same positively, or like a positive and a positive with magnets, they repel each other.
And that's the one that I like to talk about a lot, because everybody's done that. Now think about what he just said. He said, and what he meant was, say I got a magnet with a North Pole and a North Pole, right? The caps are the North Poles. These are the South Poles. If I have a North and a North, say I have 2 really strong magnets on the smooth surface, maybe a piece of glass. If I have 2 really strong magnets, I can do this. I can move this one magnet close to the other. When I get close enough, if the surface is smooth enough, they never have to touch each other. The second one's going to move away. Some kind of way, the force goes from the first object, the first magnet, to the second one and pushes it away. They never have to touch each other. So one of these action at the distance force, one is magnetic. Are there any other kind of action at the distance forces you can think about?
Gravity.
Gravity. I was going to think about that next. So here I have an object. If I let it go, it's going to fall, right? If you ask a kid, well, why did the eraser fall? They're going to say, well, that's down. It fell down. But if you think about it, we live on a sphere. There is no down. If you're on the South Pole, then down is up. There is no such thing as up or down. It has nothing to do with up or down. It has everything to do with the fact that if I have this eraser, it has mass. And the Earth has mass, and any object is attracted to another object that has mass. Things that have mass are attracted to each other. So the bigger the mass, the more the attraction. So I have this eraser, and I got the Earth. I'm standing on the Earth. And Newton says you can't have one force, there's always two. So there's the force of the Earth on the eraser. The Earth's pulling down on the eraser. And there's the force of the eraser on the Earth. The eraser's pulling up on the Earth. And of course, since the Earth is much bigger than the eraser, the Earth never comes up and meets the eraser. The Earth pulls the eraser down to itself. But again, there's a force pulling down on it, and we call that force gravity. When they send a rocket ship, they blast off a rocket ship from Florida. It starts out really slow, burns a lot of fuel, and then it starts to speed up. And as it burns off fuel, it goes faster and faster. But as it gets further and further away from the Earth, eventually it has to burn less fuel because it's getting outside the Earth's gravitational field. What they want to do is escape the Earth's gravitational field because Earth is pulling back down on that rocket. And so again, the Earth can apply a force on the rocket, and the rocket can apply a force on the Earth, but they never have to touch each other. The second action at a distance force is gravity. And there's one more. There's one more action at a distance force. What is it? We've already mentioned it today, earlier. One more.
Electrons and protons.
The what?
Electrons and protons.
Yes, exactly right. Electrons and protons, right? The same thing with magnets. These positive and negative charges act the same way. If I have two negative charges, if I bring one charge close to the other one, there's a force of repulsion. If this charge is free to move, it's going to move away. If I have two positive charges and I bring one close to the other, it's going to move away. If I have a negative and positive, it's going to pull together. Either way, I have forces acting through a distance. That third and final action at a distance force is called the electric force. Electric. So I got the force of gravity, that's an action at a distance force. I got magnetism, that's an action at a distance force. And then the last thing is I got this idea of a electric force. It's also called a Coulomb force. The electric force is called a Coulomb force. Now, there's one thing that all three of these action at a distance forces have in common. What do those three things have in common? They all have a what? They all have a blank. They all have a magnetism, gravity, and the electric force. They all have what in common?
Positive and negative.
Not that. I'll give you a hint. It begins with the letter F. Begins with the letter F.
They all have a force.
Force.
Okay.
Force.
You place force on it.
Oh.
You place force on it. 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 You place force on You play baseball on it.
Oh wait, they all have a field?
Yes.
Oh my gosh.
Yeah, field.
Think about it. Yes. There's a magnetic field. If you ever, in your high school science class, I don't know if you ever take a magnet, you can take and put a piece of paper over it, and they shake metal shavings like pepper, and they'll sprinkle the metal shavings on it and shake it around. You can actually see the magnetic field. So there's a magnetic field between two magnets. There is a gravitational field. You know, the rocket ship trying to leave the Earth is trying to escape the Earth's gravitational field. And there's an electric field that exists between charges. So all of these have fields. Now here's the strange thing. Scientists don't even know what is a field. We have no idea. We know a field, when I have these two charges, something happens to the region of space between the two charges. We don't know exactly what a field is, but we know what they do. So in physics, there's these two definitions. When you define something, you define things in terms of what they are. You try to explain what something is. But sometimes in science and engineering, we have no idea what something is, but we still want a definition. So they have something called an operational definition. It allows us to define something in terms of what it does. So we don't really know what a field is. On the physics level, on the fundamental level, we have no idea what a field is, but we know what fields do. So here's what I want you to write down. A field, electric field, magnetic field, gravitational field. A field is the mechanism through which forces are transferred or energy is transferred through free space. A field is a mechanism through which force is transferred or energy is transferred through free space. So these two objects can transfer force from one object to another. This magnet can apply a force on this magnet. They're connected by the field, and that force is transferred through the field from one object to another. The thing that the thing has in common that actually touches, I want to say reach out and touch, is this invisible field. And force can travel through that field. The same with the Earth's gravitational field. So a field, magnetic field, gravitational field, electric field, it's a mechanism through which force or energy can move through free space. Okay. That's a lot to swallow, and it's getting a little deep, but I kind of can still see how it works. I'm all right with it. All right, well, let's go back to energy for a second. And I want to just drill down a little bit deeper in that. So, most people have heard of the conservation of energy principle. I've already mentioned it one time. The conservation of energy principle says that energy cannot be created or destroyed. I can only change it from one type to another. Now, I want to change that a little bit in just a second, but when I'm talking about energy, there's only two kinds of energies in the whole universe. And I know what you're thinking. Well, hold on a second, Singleton. There's more than two types of energy. No, there isn't. In the whole entire universe, only two types of energy exist. No matter what you tell me, no matter what energy you name, I can put it either in one category or the other. Let's talk about that. There's two types of energy. One type is called potential energy. I'm going to abbreviate it, PE. And the other type of energy is called kinetic energy. I'll abbreviate it, KE. In the whole universe, there's only two types of energy. One type of energy is called potential energy. The second type of energy is kinetic energy. And so the conservation of energy says that I can't create energy, I can't destroy it. All I can do is change it from one type to another. And what they mean by that is I can change potential to kinetic, or I can change kinetic the potential, but what I cannot do is make the energy disappear. That's impossible. What is potential energy? Can anybody tell me what is potential energy?
Stored energy.
Potential energy is stored energy. Stored. That's important. Potential energy is stored energy. Potential energy is energy an object has because of its position. So stored energy can be stored because of position. Potential energy can be stored energy because of an object's condition. I can have energy stored because of an object's position. I can have energy stored because of an object's condition. And what am I talking about? Well, again, I need a prop, but I don't have a prop. Let me see. Okay, so this is going to be my weight. This is going to be my example. Actually, I need one of these things to clean my hands because I've been touching everything. These are those disinfecting wipes. Anyway, so I imagine this is a weight. And you can't see it in the camera, but let's just say it's on the ground. And I want to move this weight from here to here, from point A to point B, right? So I want to move it. Now, remember what I said earlier? I said that the conservation of energy says that energy cannot be created or destroyed. Energy is conserved. I can only take energy and change it from one form to another. I can change it from potential to kinetic. But I want to redefine that. I want to say that a different way. I want to say it a different way because of the fact that in physics, the unit for energy is the joule, but the unit for work is also the joule. So what I want to say about the conservation of energy principle is, I want to say it this way. All joules are conserved. All joules are conserved. And if I do it that way, then I have potential energy, I have kinetic energy, but I got something else that's measured in joules that's not on this list. I also have work. So now I can have joules of potential energy, I can have joules of kinetic energy, I can have joules of work. Now watch how this works. Let's say I have this heavy weight and it's sitting on the ground, my hand is the ground. I want to move this heavy weight from here to here, from point A to point B. What do I have to do to move the weight from point A to point B? What do I have to do?
Work.
I got to do work. I got to do work. Work is when a force acts through a distance. If work's happening, that means something has to move. If nothing moves, there's no work being done. So if I want to move this from point A to point B, I have to do work. So here's there's a force acting through a distance to raise it up to point B. So now, let me be more specific. I want to move this weight from point A to point B. Let's say I do 10 joules of work. So I do 10 joules of work going from point A to point B. Joules cannot be created or destroyed. Where did the 10 joules of work that I just performed, where did they go?
They're stored in its position.
Yeah.
They're stored in this position as potential energy. How do I get those joules back? What do I do? How about if I let this go? If I let this go, what happens? Now this thing starts to move, right? What is kinetic energy? What is it? Kinetic energy is the energy of what?
Motion.
Motion. Kinetic energy is the energy something has because it's moving. So, I can take an object, I can do work on the object. I do 10 joules of object, I do 10 joules of work moving an object from one place to another. those 10 joules cannot disappear. All joules are conserved. Those 10 joules of work I perform have to go somewhere else, and right now they're stored in the weight, they're stored in the object as potential energy. And if I want to get those 10 joules back, all I got to do is let it go. When I let it go, it's going to start with no motion. It's going to speed up and go faster and faster. And what's happening is, as this thing moves down, I'm getting less potential energy and more kinetic energy. Right before it strikes the ground, I have almost zero potential energy, and I have the 10 joules back now as kinetic energy. But there's a difference between KE and PE. KE is the only kind of energy that can do work. Kinetic energy can do work on something. It can make something move. If this is a weight and I raise it up and say this is a metal stake, I can drop this and hammer a stake into the ground. Kinetic energy is the only energy that can do work. PE can become KE, and KE can do work. Now, let me go through this one more time. I have a mass here. My hand is ground. I want to move the mass from point A to point B. So I'm going to do work. I got to do work in separating the mass of the object from the mass of the earth, which is my hand. So I do work on the object. But those joules of work cannot disappear. If I do 10 joules of work moving the object from point A to point B, those 10 joules, but listen to what I'm saying right now. If I do 10 joules of work in moving the object from point A to point B, those 10 joules of work that I perform have to go somewhere. They're stored in the book as potential energy, gravitational potential energy. Those 10 joules of work are stored in the object as gravitational potential energy. If I want to get those joules back, all I got to do is let them go, or let the object go, and the potential becomes kinetic. Well, it turns out that exactly the same thing happens when I work with charges. Let me show you what I'm saying.
I have a question regarding the condition aspect of potential energy.
Oh, yeah, go ahead.
So does that mean that everything technically is potential energy, right? Because if you burn something, then you're converting matter to energy.
Yeah, let me, who am I, who's talking? I gotta get used to that.
Darren.
Darren? Okay, Darren. Actually, I forgot about that, guys. Let me back up. I'm getting so excited. I'm getting ahead of myself. And hold your question just for a second. So I mentioned PE is energy an object has because of position or condition. And I explained this one, that makes sense, that I have an object. If I raise it up, it has a certain amount of potential energy. If I want to give it more potential energy, I got two choices. I can raise it up either higher, or I can make this more massive. Either way, I get more potential energy. But I never explained condition. So what I mean by that is, let's say I have I need a prop. That's not things in here in my classroom I have. Okay, here's an example. Let's say I have a wall. Here's the wall. Here's the floor. And let's say I have a spring, a metal spring. And that spring is just laying there. And I reach in here and I stretch that spring all the way over here. And then stretching the spring out here, I do 10 joules of work. And I just hold the spring right there. Where are the 10 joules stored? Well, this doesn't have anything to do with height.
It's in the spring.
It's in the spring. If I want to get the 10 joules back, I just let it go. Matter of fact, they don't have this anymore because you guys do everything on your phones, and I don't even know if they even make real toys anymore. But I'm a pre-internet baby. I was born way before the internet and all this virtual stuff. They should actually have wind-up toys. You can wind something up And what you were doing was you were turning a spring. And some of the old watches, most watches now are electric, but some of the old watches you had to actually wind them up, and you were turning a spring. You tighten up a spring, and you were putting energy into a spring. So the condition I'm talking about here was a condition of being stretched or compressed. I can take metal and bend it a little bit, and it has basically energy stored in it. And if as long as I don't deform the metal, it acts like a spring. When it comes back, whatever energy I put in and changing the condition of the object, I get that back when that spring or metal goes back to its original state. Now, Darren actually mentioned something that was quite interesting. He said, when you talk about condition, what about when you burn something? Well, Darren, you're exactly right. Where does the energy come from to turn the wheels of your car? When you start your car and you're driving down the street, where's that energy come from?
Gasoline.
The gas.
It comes from the gas. So what do you mean when you say it comes from the gas? What happens? How is that energy released?
It's
Combustion.
combusted.
Ignite.
Combustion, right? You have a cylinder, you have a piston, you have air. The piston compresses the air. There's fuel injected into that compressed air, and then they spark it, and there's a small explosion. And so that explosion causes the air to heat up quickly. And when something heats up, it expands, and the expanding air pushes the piston back up, and the up and down motion of that piston eventually causes your wheel to turn. But the story actually goes back further than that. Because if I have a can of gasoline, there's nothing stretched or compressed. What's in the gasoline that's giving me that energy? What's going on there? Matter of fact, where does the gasoline come from? Well, it actually comes from dead trees and dinosaurs, and it goes back probably millions of years. But when you burn something, you release bonds. You release energy in the form of potential energy. So yes, that's another. When we talk about condition, I can talk about the actual breaking of those atomic bombs. I'm saying atomic bombs, atomic bonds, like James Bond. It can actually give up energy in the form of heat. That's another form of potential energy. So yeah, good point. Okay, I'm getting carried away with this physics stuff, and my department chair, Dr. Whaley, he told me, he said, well, you need to skip all the physics stuff because you just need to just focus on. But I really think that I can just come and, like a lot of people say, all right, here's voltage, here's current, here's resistance, let's work with it. But I really think you need to know what this stuff is. So I'm running out of time, so let me get to the point here. Because Darren has a good point. I forgot about the condition part of the PE definition. But let me get to my point. Let me go back to this. So what I said was, if I have a mass, I can do work on the mass. I got to separate the mass from the mass of the object from the mass of the earth, which is my hand. So in order to separate the two masses, I got to do work. If I do 10 joules of work in separating the masses, then that work now is stored as potential energy. But what kind of potential energy? It's stored as gravitational potential energy. If I want to get the work back, the joules back, all I got to do is let it go. Well, exactly the same thing happens when you have charges. Let me show you what I'm saying. Say I have two charges. I got a minus charge and I got a positive charge. Now, I show this with charges with just two, but I'll tell you right now, it's really, really, really silly. Hold on a second. It's really silly to think of just two charges. You never deal with just two separate charges. We deal with groups of charges, but I'm trying to show a point here. I got these two charges, a plus and minus, and they're stuck together. I want to separate them. What do I have to do to separate the charges? I'm trying to separate them. What do I have to do? Are they going to come apart real easy? And the answer is no. Why? Because like charges repel, but unlike charges attract each other. So they're stuck together because they attract each other. So what do I have to do if I want to separate the charges? What do I have to do? Trying to separate them, what do I need to do?
Introduce unlike charges.
What did I have to do here to separate the mass of the object from the mass in my hand? What did I have to do?
Work.
I had to do work.
Force. You
Yeah, I
have
had to have the
force.
force. It's going to take some work for me to separate the charges like this. Let's say I do 10 joules of work in separating those charges to get them like this. When I have them like this, where'd the 10 joules go? Where'd they go? Well, they're stored. They're stored as, here's the answer. Let me answer my own question. They're stored as potential energy in the charge, but not gravitational potential energy. Remember, there was magnetism, there was gravity, and there was electric. Well, before, when I had the two masses, and I separated the two masses, the thing that made them want to come back together was gravity. But if I have two charges, the thing that wants to make them come back together is not magnetism. It ain't gravity, it's what? Electric force. And so, if I take two masses and I separate them, I have a gravitational potential difference between the two. But if I take two charges and I separate them, I don't have a gravitational potential difference. I have an electrical potential difference. If I take charge and I separate it, I get an electrical potential difference. And just like this mass and this mass want to come back together if I drop it, if I release this, these two charges are going to want to come back together. If I exert 10 joules of energy and separate these charges, I get the 10 joules back when they come back together. But the point I'm making is this. If I separate masses, I have a gravitational potential difference. When I separate charge, I have an electrical potential difference or a voltage. A voltage. Now hold on a second, Singleton. It seems like you're saying that if I want to make a voltage, all I got to do is take charge and separate it. That's exactly what I'm saying. That's exactly what I'm saying. Voltage is nothing more than a separation of charge. If you want to make a voltage right here, right now, all you got to do is figure out a way to take charge and separate it. If you look at a battery, your car battery, your car battery has terminals on it, and one terminal is marked positive, and one terminal is marked negative. Why is one terminal positive and one negative? Because through electrochemical action, guess what a battery does? A battery separates charge. If you have a generator, you got a generator in your car. If you got a mobile home, you might have one of those generators you plug into put gas in to power your RV vehicle. Generators separate charge. Anything that creates a voltage, all that thing is doing is separating charge. When I separate charge, I get not a gravitational potential difference, I get an electrical potential difference, and that electrical potential difference I call voltage. So I went through all of that to say this, that all voltage is charge that has been separated. All voltage is charge that has been separated. Now let me give you a more numerical definition of that. All right. So let's say I have a bunch of charge here. So I got negative charge here. And I got positive charge here. And I got an electron. Now, really, when we talk about any of this engineering or physics stuff, we can't deal with single electrons. We deal with groups of electrons. So the normal way we put group of electrons together is if we got 20 cigarettes in the pack, 12 eggs in a dozen. We have we have 6.25 times 10 to the 18th electrons in the coulomb. So imagine I have 1 coulomb of electrons right here. It's 1 coulomb. And what I want to do is I want to move those electrons up that way. So that means I got to do work. Now, this is going to be real hard because, you know, light charges do what? Light charges repel. So I got a bunch of electrons right here that have a negative charge. I got electrons I'm trying to move towards the negative. So I'm going to have to really push really hard because light charges repel. I'm going to have to do a lot of work in moving this 1 coulomb of charge up to the other negative charge. And if I do 1 joule of work moving 1 coulomb of charge, I say I have 1 volt of electricity or potential difference. So in other words, voltage equals the amount of electrical work being done separating the charge divided by the amount of charge. So it's work per unit charge. So V equals we'll use a W for work. W over Q. So there's a formula for you that. Now on Blackboard, I don't know if you guys looked in the week 2 folder. I got a bunch of stuff up there. And one of the things, I don't have homework 2 up there. I need to put that up there tomorrow. But I do have a supplementary quiz up there. And this is going to help you with that supplementary quiz. So write this equation down. And I think like the last 2 problems, you'll notice on that supplementary quiz, whenever you get a chance to look at it, I think if you turn it upside down, I have the answers to certain problems. And I have the answers to certain problems because I want you to, you're doing it the right way. But you got to work them all out. I think the last 2 problems on the page, you'll need this equation to do the last 2 problems. But if you look at this, remember work has the units of joules. Charge has the units of coulombs. So 1 volt is a joule coulomb. That's the way to think about it. But this formula, if I know how much work I got to do in separating charge, and I know the amount of charge, I can figure out the amount of voltage. But what I want you to remember after we walk away from this camera, I want you to remember that voltage is nothing more than the separation of charge. If you have anything that produces a voltage, all that thing is doing, I don't care what it is, if it's producing the voltage, what it's doing is it's taking charge and it's separating. Batteries separate charge. They're really good at separating charge. So, what is voltage? Voltage is a separation of charge. Now, this isn't going to work this way, right? Because if you think about it, I really got to push this charge up towards the negative. It's going to want to go the other way. Let me flip this around. I want to show you something else. So the first thing I'm going to do is create a voltage, a potential difference. Not a gravitational potential difference, but an electrical potential difference, which means I'm going to separate charge. And all the electrical potential difference is, all the separation of charge is voltage. So let's say I take some charge and I separate it. I got positive charge here, and I got negative charge here. Now, I'm going to first do this with just 1 electron, but then I'm going to change it in just a second. So I'm going to put 1 electron right here. And I got a bunch of positive charge here. I got a bunch of negative charge here. I got charge that's been separated. So this is an electrical potential difference, or voltage. A separation of charge is a voltage. So now I got a voltage right here. If I hold this electron right here and I let it go, if it's free to move, what's going to happen? happen? I got to make sure, but when you guys don't say anything, I got to make sure my camera didn't cut out on me. So I got the electron here. It's free to move. When I let it go, what will happen? Which way will it move?
Move to the positive.
It's going to move to the positive. It's going to move this way. Right? Everybody agree with that. Now, what causes it to move? If I have something that's not moving and I started to move, the only way I can start something to moving is I got to do what? I have to apply what?
Work.
Okay. I think I heard it. What'd you say?
Force.
A force. Okay, well, how am I applying the force to this? There's nothing touching it. How am I if it takes a force to cause this electron to move, and I'm not touching it with anything, how's it moving if there's nothing touching it to apply a force to it? How's it moving?
Like charges repel.
Okay. Like charges repel is kind of right. Because remember we said there was two kinds of forces, right? Two classes. There were contact forces. Well, obviously, that's not this. But the other kind of forces are what? Action at a distance force, and that's this one right here. So I'm dealing with electric things that have charge. One object can exert a force on another object, and they never have to touch each other. What happens, though, is there's a what? We play baseball on it. There's a what?
A field.
A field. There's a magnetic field between two magnets. There's a gravitational field between two masses, and there's an electric field between two groups of charges. So here's what happens. That charge is sitting there. Now you know like charges repel and unlike charges attract, but there is no repelling or attracting unless there's a force pushing it away to repel or pulling it to attract. So how does this thing reach down and pull this thing up to cause the attraction? Or how does this thing reach up and push it away to cause a repulsion? The answer is there's a transfer of forces. Remember we said a field is used to transfer forces or energy. And so what happens is there's an invisible field between two masses. There's an invisible field called the gravitational field. You know it's there. Between two magnets, there's an invisible field called the magnetic field. You know it's there. You can even feel it when you take two magnets and you play around with them. And between two groups of charges, there's an invisible field called the electric field. So when I separate charges to make a voltage, what I get is an electric field. I'm drawing it in red. And that's called the E field. And that's short for electric field. And since this charge is an electric field, and that electric field can carry force, the electric field actually forces the charge to move this way. So it works like this. I separate charge. When I separate charge, I produce a voltage. Between the two regions of charge is an electric field. If I take any charged particle and put in that electric field, it's going to experience a force because that electric field can cause forces to act on the object to cause it to move up or away depending on the charge I put in the field. So let me go back to this because I had just one electron there. Now I'm going to put a whole bunch here. I'm going to put 1 coulomb of electrons here. And I'm going to put a line right here. This is like a finish line. And here's your eyeball. And I got this charge right here, and I'm holding that charge, and I let it go. Well, if 1 coulomb of charge passes this point in 1 second, then I have 1 ampere of current. In other words, if I just have charge sitting there, I just got charge. But if I make that charge move some kind of way, now I have charge that's flowing. I have electric current. So all electric current is charge in motion. And if I write it as an equation, current is charge per unit time. Current is charge in motion, or current is charge per unit time. So the way we write that is, we use an I for current. We don't use a C, we use an I. And what do we use for charge? What letter? What do we use for charge?
Q.
Q for charge. And for time is always a lowercase t. So here's another equation that'll help you. You write it down. So far we got a voltage is work per unit charge. And now current is charge per unit time. So this right here, the unit for that is coulombs. This right here, unit for that is seconds. So current has a units of coulombs per second. But 1 coulomb per second, we call that an ampere, or amp for short. So 1 amp is 1 coulomb per second. You guys are getting quiet on me. We're almost done. Let me go back to this file, and I want to do this practice. Let's look at this practice. I think we did everything on here except for number 4. Look at problem number 4. See if you can figure that out. It says you have a charge of 5 coulombs. So the charge is 5 coulombs. So I have a charge of 5 coulomb flows past a given point every 0.5 seconds. So the time is 0.5 seconds. How much current flows in amperes? That's the question.
10 ampere.
Does that make sense? Yeah. So using this equation, I have, says I have 5 coulombs. So Q is 5 coulombs. The time is 0.5 seconds, so 0.5 seconds. So if I divide 5 by 0.5, I get 10 coulombs per second. 10 coulombs every second, but a coulomb per second is an amp, so the current is 10 amps. And what we've talked about so far is this. I'm not going to write on the board. You guys just have to write it down. What we mean by voltage is, a voltage is a separation of charge. When I separate charge, I get an electrical potential difference, and that electrical potential difference is called voltage. When I have separated charge, when I have a voltage existing in the region between the separated charge, I always have an electric field. If I put charge that's free to move in the electric field, then that electric field can cause a force to act on the charge that's free to move and cause that charge to move. And once it's moving, I have electric current. And because it's moving, it has kinetic energy, and that moving current, kinetic energy can do work. That moving current can do work. It can do the work of lighting up a light bulb, turning a motor. It can do whatever work you want it to do. So voltage is a separation of charge. Current is charge in motion. It takes a voltage to make a current. There's a cause and effect relationship. It takes a voltage to make a current. You should be able to go through that whole story. I got to separate charge. I get the electric field. I put something, charge is free to move in the field. And because of that field can transfer a force to the charge that's free to move. It can cause the charge to move. If it's moving, now I have electric current. There's a cause and effect relationship. The cause of a current flow is a voltage. You cannot have a current without having a voltage. The cause of a current flow is a voltage. Now, Anybody have any questions for me? Because we went through a whole lot tonight, and we're not even done. Anybody have any questions? All right, well, there's one more thing on here I need to talk about. Well, actually a couple things. There's current, control, and protection. I'm gonna let you read about that in your book if you have a book. There's resistance. Under resistance, the origin of resistance, the resistor color code, variable resistors, and wire resistance. Well, we actually do that in lab. I'm not gonna talk about that tonight because I do a whole lab on resistance where we go into detail on color coding and the resistance of wire. I do want to say something about the electric circuit, which is the very last thing on here. So with the exception of resistance, we pretty much talked about everything on this topic sheet that I want to talk about. Let me show you one more thing, and then I'll take any final questions, and then we'll call it a night because you guys have been listening to me talk for a long time. I want to talk about an electric circuit. So we talked about voltage. I gave you a definition of voltage. All voltage is charge that's been separated. Voltage is a separation of charge. We talked about current. All current is charge in motion. Charge cannot move unless there's something to make it move. And what makes a charge move? You got to put it in an electric field. How do you get an electric field? You got to have a voltage. So voltage causes current, cause and effect. Voltage is the cause of a current flow. And then I didn't talk about resistance. We'll do this in lab. But you kind of already know on a certain level that anytime something moves, there's always something to stop it from moving. Anytime something moves, there's always something to stop it from moving. So usually in the macro world, we call it friction. If I roll a ball down the hallway, I can roll the ball as hard as I can. Eventually, it might hit the wall at the end of the hallway. But let's say I had a hallway that never ended. I got an infinitely long hallway, and I roll the ball as hard as I can. Eventually, that ball is going to stop because friction is slowing it down between the floor and the ball. Friction produces heat. So some of the energy that I put into rolling the ball away from me goes into the heat, the friction. Friction causes heat. So resistance is the electrical equivalent of friction. If there's current flowing, resistance wants to oppose that current flow. Now I'm going to go into more detail about what resistance is in lab, but this is the big three. Voltage is the separation of charge. Current is charge in motion. Resistance is opposition to current flow. For each of these quantities, there's a symbol we use to represent them. And I want to show you. And I'll explain these later, but just briefly, if I want to represent a separation of charge, a voltage, I can do it like, there's three ways to do it. I can do it like this. I can do it like this. Or I can do it like this. So these are three ways to represent a voltage graphically. You can use either one of these. Now, strictly speaking, I'm not going to go into it now. I think I'll go into it next week. But strictly speaking, these are different. This is a battery. This is a cell. And this can be either or. But for now, we can use any one of these. If I want to represent the voltage, I can draw one of those to represent the voltage. So let's say I have a voltage of 15 volts. I can draw maybe this. Put a plus and minus sign on it. The long line is always positive. The short line is always negative. And I can just say, all right, this 15 volts, I can write it like that. If I want to represent a current, graphically, I use an arrow to represent current. If I want to use a symbol to represent resistance, then it looks like the end of a saw blade, like this. That represents resistance. I can draw either like that or straight up and down. So what I can do is I can draw what we call a circuit. I need a voltage source, so I can do this. I got a resistor. Now, the resistor could represent a light bulb, a microwave, a refrigerator, or actually it could represent anything because everything has resistance. So we usually just show everything as a resistor, at least right now. So I can just show it like this. So here's my resistor. And then to make this a circuit, I want to just draw these wires connecting the voltage source to the top of the resistor and the voltage source to the bottom of the resistor. When I do this, this is called an electric circuit. And we use diagrams like this to show how things are connected electrically. We got a lot more symbols we got to learn, but these are the basic two. And one last thing, let's think about, let me go back to current just real quick. You know how it works now. I got to create a voltage by separating charge. So let's say I got positive charge, and down here I got negative charge, right? I got the electric field. Electric field always goes from plus to minus like that. That's my E field. And then my electrons are going to move to make the current. These are my electrons. They're going to move that way. So what I'm saying is, in this picture, if I want to draw the current flow, I draw it like this. Electrons go from negative to positive. Electrons go from negative to positive. So that's called electron flow. Well, you're probably not going to like this, but we make up another type of current flow. We make up, we don't follow the actual path that the electrons take. We assume that the current goes the other way. Even though we know they go from negative to positive, we act as if the current is actually going this way, from positive to negative. Now, I don't want to go into why right now because I'm tired and it's almost like 9:15. I'm running out of gas. If you remind me, I'll explain next week about this. But there's two kinds of current flow. There's the actual current flow, which is called electron flow. But then there's this made-up current flow where we reverse it, and this is called conventional current flow. So I don't know if you have your textbook or not, but if you have your textbook and you look at the current, if you look at the front cover of the textbook in small letters, it'll say conventional current version or something like that. You can buy your textbook in either electron flow, and they'll show all the currents in the book going the right way, from negative to positive, or you can get the one that you got with this conventional current flow, and they'll show the current going from positive to negative. It doesn't really matter as long as you're consistent with whatever you're doing, but there's a reason why they do that. As I said, I don't want to go into it tonight. If I can think about it next class, I'll do it, or if you remind me, I'll explain the difference between the two, why there is a difference, but I don't want to do it tonight. So I'm ready to, I'm ready to end this for tonight. I'm out of gas. Anybody have any questions or comments on anything we talked about tonight, anything that wasn't clear, I need to revisit, any concerns, anything you want to tell me before I sign off?
I thought it was pretty good, and I don't have any questions. I got a lot of notes and some good pictures in.
Good. Who is that talking?
Michael Sparks.
Okay, Michael, you get an A for the course. You don't even have to finish. I like that.
Sweet.
Michael Sparks. And I like that name, Michael Sparks. That's an electrical name.
Yeah, I didn't really think about that till now. That's kind of cool.
Yeah, your name fits your major. I love it.
Thank you.
Thank you, Michael. Thank you. I really appreciate that. Well, guys, if you don't have any questions, you guys have a good rest of the week. Please stay safe. The numbers are actually going down. The COVID numbers are dropping. I'm happy about that. If they continue down, then we'll be able to, at some point, maybe next week or the weekend, we can meet face to face for some laughs. We'll see. So I'm happy they're dropping. But you guys still stay safe. If you need me for anything or have any questions, please send me a text. And other than that, I will see you guys 1 week from today online.
All All right, thank you. Good night.
Today we have
Thank you. Have a good
we
night.
have a lot to learn things, and I would like to make sure that this week, what are the this week assignments?
Mm-hmm.
Yeah,
What about the assignment?
yeah. So I saw the lab assignments for
Yeah,
today. Yeah.
yeah. Did you see the lab assignment?
Yes.
Yeah, so that's due, I think, tomorrow. I meant to mention that to everybody, but
Yeah.
yeah, that's on Blackboard. You don't have to come in. That's all done at home. And there's a sheet that you just go through. Watch my video first,
Mm-hmm.
and then just try to, go through that. It's called the DC Construction Kit. It's pretty cool.
Yeah.
So play around with that, and then answer the questions, and it should be pretty easy. But if you have any questions, you can always send me a text.
Yeah. So I would like to make sure that next week is the lab. Or
Well, I don't know. I don't know if we're gonna have a lab next week. I want to see.
yeah.
Yeah, I want to see how. We're probably gonna do another lecture, and then after that, we'll have a lab. I feel like I want to do online one more week because the COVID numbers are dropping. So I'll probably do one more week online, and then that next week we'll spend it and we'll do a lab after that. But not next week.
Also next week we don't need to come to the campus. Oh,
No.
okay.
We'll say the week after. The week after.
The week after.
Yeah.
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 Okay.
The supplementary quiz, is that going to, like, should we hand that in during the lab, or should we scan that in before?
No, just when you come in. We're not gonna meet next week. I think I'm just gonna push it one more week, and then we'll come in the week after that. Just bring it what you did.
Okay.
So I don't know if there's a due date on it, but just bring it in when you come in for the first lab.
Awesome. Thank you.
All right, buddy. Thank you, guys. Thank you, and I will see you guys next week.
Take it easy.